Let's get started. Okay, now, y'all, this actually came, I think, from Finland, and I got this idea from a well-known channel that deals with constant absorption was the language that kept getting used. But anyway, this was in Finland. I don't know if it was the Finnish Olympiad, but this is what was recorded at Dr. Penn's site. Finland, I think 2001. And in fact, it was one of those year problems where this number was 2001, okay, and he worked through the problem. Very tedious problem, but it's kind of interesting because we're trying to find all the natural numbers in such that this quotient evaluates to a natural number, and I take a natural number to be 1, 2, 3, positive integers. Now, so we go ahead and assign a value of m, a natural number, to this quotient, and of course, we can rewrite it like this. We can rewrite it like this as an equation form, where it's perhaps a little bit easier to work with. Now, the nice idea, the first idea here is just to multiply the left-hand side and the right-hand side by this conjugate. If you want to call it that, conjugate, just flip the sign. The reason why you do that is you can exploit the difference of two squares formula. Okay, so this is like a plus b times a minus b, so you get a squared minus b squared. And of course, you have to do that to the right-hand side. And I think you get basically an equivalent equation. Any solution to this is going to be a solution to this. I don't think there's extraneous solutions here. But in any event, it turns out to be useful just to give this green expression a name. We call it A. So that's the first constant that absorbs this expression right here. Now, you probably could carry this all the way through the problem. But anyway, this is the way he did it. Okay, so we have equation 1 right here. Okay, now if you keep going here, we're trying, if we have this big term here, 193 squared n squared, that we got from completing the square up here. So we're going to try to eliminate that. And again, I wouldn't know to do this on my own. But what we do is just multiply n squared plus 14, which is part of the original expression, by 193 squared. And of course, that produces this term. And so what we get is an equation 2, and we call this constant b is just 193 squared. But it's just kind of nice to carry letters around instead of numbers in this particular, for this type of problem. And again, I wouldn't have known to do any of this. So we have two equations here, and notice that if we subtract them from each other, we do eliminate this. And so when you can do it in any order, I thought this was most convenient. But notice we get this expression n squared plus 14 times the quantity b minus a. We don't have to worry much about the value of b minus a, it turns out. Okay, so but what we can notice here is that for this equation to hold, or for n squared plus 14 to have any solutions, it's going to have to equal to divisors of this prime factorization. And y'all, this was tedious to find, okay? But I won't bore you with that. It was very tedious, time consuming. So we have n squared plus 14. And again, we're not worried about what this equals. We just know that n squared plus 14 has to be a divisor of this number here. Okay, but this number has a prime factorization of this, okay? 2 times 3 squared times 5 squared times 19 times 61. Again, very, very time consuming. I made a mistake the first time I did it. I actually checked it, to make sure I got it right, so I wouldn't be showing you guys a bunch of rubbish here. But notice right here, we can kind of be sort of selective, because right here you have no idea what's going on with this large number, but here at least you have an idea of what its divisors are by looking at this prime factorization. Now notice right here, if you pick the factors 2, 3, and 19, which would be a divisor, let's write this down. 2 times 3 times 19. That's actually equal to 114. Okay. Now, again, believe it or not, I noticed that because I noticed this ends in 14. And, of course, this will imply that n is equal to 10. Okay. So this would say that n is equal to 10. Okay. Now, you may want to circle that, but we don't really know if it's a solution yet because we multiplied through by something that made the equation bigger, and perhaps we introduced extraneous solutions. So let's go down here and take our n equals 10 and put it in right here. So if n is equal to 10, okay, again, folks, if you substitute n equals 10, again, this is checking. This is our original expression that we were trying to make an integer. You actually get n equals 10. For n equals 10, you actually get that this is equal to 20. Let's see here. N equals 10. You get 17 right here, I believe. Okay, for n equals 10. I believe, let's see, am I right about that? N equals 10. Let's do the calculations. 1930 plus 208 plus 114. Okay. Y'all, I think that's right. I'm not, gosh, let's see. Equals 4. I believe that's right. Okay. Now, again, y'all, I think this is right. I don't have my calculation, but I'm pretty sure that's what I got. So for n equals 10, that evaluates to 17. Now notice another possibility right here would be n squared plus 14 equals 2 times 3 times 5. Okay, so 2 times 3. And y'all, again, this was very time consuming, all of this. 2 times 3 times 5 is equal to 30. And I don't even know if I have all the solutions. These are the only two that I found. Okay, but that would imply that n is equal to 4. Okay, that would imply n is equal to 4. And if you substitute n equals 4 right down here, for n equals 4, y'all, I got that this was equal to 26. Okay. And I've double checked that quite a bit, so I'm pretty sure I got this right. So far, folks, these are the only two solutions I know. I'm not saying these are the only solutions, but they're the only solutions I've found so far. Now, to give you an idea how this went, and again, I'm leaving out quite a bit of what I did, but notice right here, you know how many divisors there are of this number if you just take, this is an understood exponent of 1 right here, exponent of 1 right here. And there's a well-known result that says you can just multiply these exponents incremented. That is 2 times 3. And y'all, I'm just inking all of these exponents. Okay, times 2 times 2. Now, folks, I believe that, let's see, what is that, 72? 4 times 3 is 12, 36. Yeah, that's 72. And y'all, what that means is there's 72 divisors. Okay. There's and notice that 114 and 30 are just two of these divisors. 30 and 114 are divisors of this number just by the prime factorization. Okay, so actually working with the prime factorization is easier. You don't have to do any big calculations. Okay, but in any event, that's all I know at this point. I do know that these two values are solutions to our original problem. They make the expression be a natural number. So if you guys can find any more, let me know. But until now, I'm thinking this might be all of them.